today's seminar session of the HIF program. We'll have as a speaker Miloš Kurilić from the University of Novi Sad in Serbia, and he will talk about reversibility of definable relations.
Thank you. Well, what's going on? Oh, it is impossible to use both things. Aha, I see. Oh. Okay, I will concentrate on it.
No, you can, when you turn it down again, right, then you put it down.
I see. Okay, thank you. So the plan is, first I will talk something about reversible relational structures. This is joint work with my PhD student Nenad Morača. And then about reversibility of definable relations with parameters, reversibility of all definable relations without parameters, and about linear orders in which all definable relations are reversible. What is reversibility? This is a property of mathematical structures which seems to me very forgotten in some way, although it is a basic property, in fact, in the sense that a lot of basic structures, in fact, have this property. And so let us give reversibility a chance. Reversibility was first considered in general topology. It was first considered by Rajagopalan and Wilansky in 1966, and about 20 years after by Doyle and Hawking. The definition is, we say that first the function f, which maps a topological space X into topological space Y, is a condensation if and only if it is a continuous bijection. And the space X is reversible if and only if each condensation, its self-condensation is in fact a homeomorphism, in fact automorphism. So each continuous bijection from X to X is in fact a homeomorphism. There are trivial examples. First, we have discrete spaces, it's clear. Anti-discrete spaces. These are trivial examples. Also, compact Hausdorff spaces. Compact Hausdorff spaces are reversible. Why? If you have a continuous bijection, it must be closed, and so it is a homeomorphism, and that's it. So very important spaces are, in fact, reversible. Now, we go to, also a lot of minimal and maximal topologies. Minimal and maximal topologies, in the sense that they are minimal or maximal with respect to some topological property, maximal connected or minimal Hausdorff, and so on. Now we go to our business, relational structures. So first, some notation. It is standard, of course. We observe a relational language. We have art, it is a signature, X is a non-empty set, and intel of X is the set of all interpretations, which are sequences of relations, of course, of the language over the domain X. By mod L of X, I will denote the set of all L structures with the domain X. Now, again, very well-known things. This int L of X, the set of interpretations ordered by the inclusion, is a complete atomic Boolean lattice. And for two interpretations, we will write, this is a beautiful notation, that sigma is subset of rho is subset of sigma, but it means that pointwise it works. A complement of interpretation is also defined pointwise. The zero of this Boolean algebra is the sequence of empty relations.
Sorry,
Yes?
what was this again? LX?
Interpretations. Simply a sequence of relations of the corresponding arities. You know, it's trivial. And one, one is the sequence of all full relations. In fact, the sets x to the power ni. Also, standard definition and power of function is the mapping. Here must be x. Of course, this is a mistake. Xn to xn defined in this way. And we define direct image of an interpretation, again, pointwise, coordinate-wise. Now, what's going on with reversibility? So, definition is the following. If we have x and y models of L with the same domain, a function f, no, this is not important. A function f from x to y is a condensation if and only if it is a bijective homomorphism. So the same thing, we have continuous bijection, bijective homomorphism, homomorphism is standard of continuity. Now, a structure X is reversible. If and only if, again, each condensation is an automorphism. So each bijective homomorphism is an isomorphism, in fact, automorphism of the structure X. And so we will say also that the structure X is strongly reversible if and only if the automorphism group is the whole set of all bijections, the symmetric group, in fact, of X. Some examples. First, of course, we have this empty structure with all empty relations. Of course, we have 0, which is the set of all maximum relations. And we have linear orders. They are reversible. Why? If you have a linear order and bijection, which is homomorphism, which means that it is increasing, it must be automorphism because it is totally ordered, and it is a standard thing. Now, these are trivial examples completely. We would like to find some non-trivial examples but so well, first equivalence of reversibility. I'm sorry. These equivalents are very clear. A relation, in fact, interpretation rho is reversible if and only if the isomorphism class is an anti-chain in this Boolean algebra, if and only if there is no smaller relation sigma, which is isomorphic to rho, if and only if there is no larger relation sigma, which is isomorphic to rho, and condition E, each permutation which, well, this implication holds, it's clear. By the condition C, we have the tournaments are reversible binary structures. It's completely clear why. If you have a tournament, this is a digraph such that for each two nodes we have one arrow. If we delete one arrow, it will not be a tournament, so it is not isomorphic to the original structure. So there is no smaller structure which is isomorphic. Now, now this is a method for constructing for detecting some reversible structures. So if phi is a set of formulas, the smallest set of L formulas such that it contains all positive formulas, which means these are formulas without negation, and negations of atomic formulas are allowed, and it is closed under finite disjunctions, arbitrary conjunctions, and under the universal quantification. Then, if T is a theory from phi and has models of size then each interpretation rho is contained in some maximal element T of this poset, and T is a reversible interpretation. What does it mean? So we have this Boolean algebra int of interpretation, int L of x. Here is it's 1. This is the sequence of full relations. Here we have the sequence of empty relations. And now we have a theory T, and here are the interpretations of this theory, which means that if rho is here, which this means that x rho is the model of T, for example. Okay, we will see the examples. And the theorem said that for each row here, there is a maximal element here of this class of interpretations, which is reversible. This is the point. Above each, there is a reversible one. So if we take posets here, for T, we take T poset, which can be axiomatized by irreflexivity and transitivity. This is subset of phi. It's clear. It's completely clear. We have negations of atomic formulas, and that's it. So what we obtain here, which are maximal interpretations in the class of posets. These are linear orders. In fact, this is order extension property, that each partial order can be extended to a linear order. This is axiomal choice. That's it. So, so we go. So the last theorem can be regarded as a generalization of the order extension property principle. And now, we obtained here for the class of posets, in fact, corresponding relations, we obtain linear orders. But for linear orders, we know that they are reversible. We did not obtain new things. How to obtain new things? So, in fact, the idea is that structures omitting some finite substructures, for example, like triangle-free graphs or something like that, Hanson graphs, are in fact reversible. And this proposition establishes that. So, this is a completely technical thing. If we have a finite language, then for each finite structure f, there is a formula which witnesses that f embeds into the structure. This is the first part of that. And its negation is in our class phi of formulas. So, excellent. We have, in fact, maximal elements and reversible structures of this theory. T can be any theory which is consistent, in fact, with that, which has models. And some examples are, first, maximal Kn-free graphs. For N3, we have triangle-free graphs. A graph is called Kn-free if it does not have subgraphs isomorphic to the complete graph of size n. N is an integer, of course. So if we take graph theory, irreflexivity and symmetry, then these two axioms you can see are in our class phi. LB is for L binary. It is not something new. So this class has maximal elements and they are reversible. There is a lot of them, of course. For example, the star graph, it's a trivial example. The star graph, we take simply something like that. There is a distinguished point x, which is connected with all other elements, and it is clear that this graph is maximal triangle-free graph, because if we add an edge, it obtains a triangle. So it's a trivial example. Also, triangle-free graphs, or more generally Hanson graphs, have this property. It is not trivial, it's a theorem. All Hanson graphs are reversible, which means that each bijective homomorphism is, in fact, isomorphism. It is interesting in the light of Lachlan and Woodrow classification of ultra-homogeneous graphs that, for example, radograph is not reversible. Why? Because if we have radograph and delete one edge, we will obtain isomorphic copy. In fact, again, a radograph, and all radographs are isomorphic. It's omega categorical, so on. So ultra homogeneity and reversibility are unrelated. Hanson graphs, and also empty graph. If you take empty graph, this is here, this empty. So it is, of course, reversible, but it is not maximal, which shows that it is not true that all reversible are maximal. Maximal are special reversible structures. Okay, more examples. Wow. I will be very fast. Maximal graphs without some cycle subgraphs. This is another example of application of this theorem. For example, we will obtain, for example, if we are forbidding C3, C4, C5, and so on, we will obtain graphs without cycles. And maximal ones are trees. If we forbid C3, C5, C7, we will obtain bipartite graphs, which are, we have two sets of nodes and no edges in between the nodes in the same set. And maximal such graphs are complete bipartite graphs, which means that there is a partition into two sets such that each from here is connected with each from here. It's clear that this is a reversible structure when if we delete one edge, we will lose this property that each from here is with each from here. And finally, maximal graphs of degree less than equal n. I will not read all these things, but this is a simple application of the previous theorem. Degree of node is the number of neighbors in the graph. So that's it. Now I run to reversibility of definable relations. This is the point. This is the title of my talk. So what's going on here? If I have a structure, for example, linear order. Stop. I know that linear orders are reversible. But what's going on with sets which are with relations which are definable in the linear orders? What does it mean? For example, the so-called betweenist relation. This is a ternary relation which says that B is between A and C. A and C can commute, of course. This is a ternary relation, and it is a question, is it reversible? Linear order, the original structure, original relation is, but is this betweenist reversible? Some relations are always empty, which is definable by 0 equal 1, or x different from x. Or the full relations is always in each structure definable because it is definable but x equals x. But what's going on with betweenists? Now definition, again, if X is an L structure and L prime is sublanguage of L, contains some of the symbols, and A is a subset of X, then by D, with these four subscripts, L prime X A n is the set of all subsets of X to power n, definable in the structure X by L prime formulas with parameters from A. This is notation which I need. That is the sets of the form, of course, this is a definition of definable sets with set with parameters. Phi is a formula. A bar is an
L prime.
L prime, yes, L prime. Examples, DLXX is the collection of all sets definable in the structure X, which model theorists call definable sets. DL empty X empty is the collection of relations on X which are definable without parameters, because of that, or O definable by an L empty formula, the formula of the empty language, which includes only the equality. That's it. And now, some ambitious question. First, if we define rev n of x, it is a set of all reversible n- ary relations, and rev of x, the union of all arities of reversible relations. The question is, first, which relations definable in a given structure are reversible? It's a very general question. For which structures we have that all definable sets are reversible? for which structures we have that all definable, so without parameter sets are reversible. These questions are very natural. First, I comment on reversibility of all definable sets. It is a very strong condition. First, if we take integers, this interval minus infinity 0 is definable. It's definable. 0 is an element, it's a parameter. And it is not reversible. Why it is not reversible? It is a unary relation which is both infinite and co-infinite. So we can take one element and it will remain isomorphic. So it's a unary relation, unary. Infinite, infinite. We take one element from here, and it is, of course, isomorphic. We will easily find the projection. Necessary conditions. All definable sets are reversible if all the sets are reversible, which is a strong condition. Then, first, trivially, all the relations must be reversible, and X must be a minimum structure, which means that each definable subset of X is finite or cofinite. So we are in the world of minimal structures. Less ambitious questions are, if we have a given definable set, is it reversible? So characterization is this. D phi A defined there is reversible if and only if for each permutation of X which satisfies this condition, which is very similar to preserving phi, but not exactly, because here is A again, not phi of A. This is the difference.
F.
Sorry?
You said phi of A.
F, sorry. Yes. We don't have F here. If F is here, then this is preservation of the formula. If we have implication, then we should have equivalence here. This is in fact rewritten condition that if F of rho is subset of rho, then F of rho must be equal to rho. That's it. But only with formulas, definability, and so on. So this is a technical lemma which says when we can move that F, this is direct image of the definable set, when we can move that F to parameters. This is a technical stuff. But this equality holds if the formula phi is absolute under F, which means that phi preserves phi in the, F preserves phi in both sides. There's an equivalence. And now there's a theorem which shows it is a sufficient condition that the definable set is reversible if for each permutation which satisfies this is in fact that, we have first this condition from the lemma, and the second that each permutation of X which fixes pointwise the set X without the set of parameters and its direct image, and for each k from integer, natural number, we have that G can jump here. Very technical, but it will, well, this holds in particular if the formula phi is absolute under all permutations. And we have a corollary that for each language and each structure, all definable sets in the empty language are reversible. And also that the class of sets which are definable in the empty language without parameters coincides with strongly reversible structures, which means that out of X is equal to sim of X. Proof: each L-empty formula is absolute under each permutation, so we apply the previous theorem and that's it. So the situation is, we have reversible relations, we have definable relations. And which are reversible always? These strongly reversible, these definable in the empty language with parameters, also always reversible, and of course in some structures we have relations which are not reversible, of course. The question is, when the Lx empty is irreversible, one of these questions from the beginning. Now, we turn to relations. No. This is examples. This is example. If we, how these relations look like. Since the theory of infinite sets has quantifier elimination, we can assume that the formula phi defining this definable set is quantifier free and in the disjunctive normal form, of this form. So these members of this disjunction are such conjunctions, and here will be the parameters appear. Now, our definable set is finite union of sets defined by these conjunctions. An example is trivial. We take omega, and which are definable subsets of omega square with one parameter. First, it is one singleton. The second, this vertical line without the singleton. Third, this horizontal line without the singleton. And finally, diagonal without singleton. And the fifth is the complement of all of this. The Boolean algebra of sets definable with parameter A has 32 elements, and these 5 are its atoms, in fact. Of course, we can go with this A everywhere. We can take 3 parameters or 15 parameters, and then we will obtain very complicated sets, and all of them and their intersection. This is Boolean algebra, in fact. And we obtain a lot of such. So these sets definable in the empty language are not simple at all. They can be very complicated. So all of them are reversible. This is a theorem which sounds trivial, but it is not. So as a consequence of the previous theorem, we have such characterization for unary languages. Unary languages are simple sometimes if a language is unary, if and only if all these arities are 1. So unary structure is in fact something like you have set and some subsets of, it's like topology, but not topology, sequence of subsets. If L is a unary language and X an L structure, then all definable sets are reversible if and only if all the components are reversible, if and only if all the components are finite or cofinite. One direction is trivial. In 4, if all of them are reversible, the structure is reversible. It is easy to prove it. For the another implication helps the previous theorem. You include some parameters and so on. Now we go to reversibility of relations without parameters, defined without parameters. And now we assume that X is a model, that phi is a formula, and d phi is a set defined by phi. Without parameters, we don't have parameters anymore. So characterization is that d phi is reversible if and only if each phi is absolute under each permutation which preserves phi. If it preserves, then phi is absolute. Absolute is equivalence, and preserving is implication. And less ambitious question is, for which structures we have that all O-definable, which means without parameters, relations are reversible. First, necessary conditions, again, all the relations, all the components must be reversible, and now each O-definable subset must be finite or cofinite. One sufficient condition is that the structure is monomorphic and has quantifier elimination. Namely, the structure X is M-monomorphic if and only if all its substructures of size M are isomorphic, linear orders, for example. If you have a linear order, each three-element subsets are isomorphic. It's trivial stuff. Structure is monomorphic if and only if it is M-monomorphic for each positive integer M. And now the condition providing that all O-definable subsets are reversible relations is that the structure is monomorphic, for example, linear order, and its theory has quantifier elimination, which is a very strong condition, in fact. So, but we can apply this theorem to dense linear orders without endpoints. It's clear. They are monomorphic, have quantifier elimination, the end. So, in addition, if we have a dense linear order, for example, rationals or reals or irrationals or whatever you want, rationals plus irrationals plus reals plus, it must not be homogeneous. Then each countable relational structure which is definable in this ordering, which means that all its relations are definable in the ordering, is reversible. This is a very large class. It is reversible, and also it is omega categorical. Why? Because if something is B-definable with something which is omega categorical, it must be omega categorical. It's a standard theorem from Hodges. Now, one can think that omega categorical structures should be reversible, for example. No, the answer is no. And example is very simple. A countable omega categorical linear order which contains relations which are not reversible. We take a shuffle of 1 and 2. What does it mean? We divide the set of rationals into two parts, disjoint parts, which are dense. It's easy to do. And now each element, instead of each element of A from Q2, we put 2 points. So it will now have dense jumps. This is shuffle. This is shuffle on 1 and 2, because this first I didn't change. It has the point remains 1 point, and this changes each of its points. Each of its points are 2 points. Is multiplied, or okay. And what's going on here? Well, this linear order is omega categorical. It is a standard theorem of Rosenstein, characterizing all omega categorical countable linear orders. They can be obtained from 1 by finite application of addition and shuffle operation. This is shuffle operation. Finitely many, and you add some orders and so on. So this is a omega categorical. Why it is not reversible? Well, the formula which witnesses that is the formula saying that U and V are different and there are no elements between them. These are guys from Q2. And which relation we obtain? We obtain the relation which is a graph having infinitely many points of size 1 and infinitely many points of size 2. Of course, it is impossible to write it because the sets are dense. And now this binary relation, this is a graph relation, it is not reversible. Why? Because I can delete this edge and it remains isomorphic to original. I have infinitely many singletons, infinitely many doubletons, and that's it. Now, one combinatorial condition which implies that definable relation is reversible. It's a bit complicated when it is written in this way, but what does it mean? It means that, in fact, for example, if we have binary case, that this definable relation d phi, the first condition says that it does not intersect the diagonal. In n-ary case, we have n-ary diagonal. This is the set of n tuples where at least two members are equal. And the second said that for each, there is a natural number, or it can be 0, of course, but this is trivial, that for each n tuple from out from the diagonal, exactly k many permutations of that n tuple satisfy phi. This is geometry, in fact, some kind of that. In particular, is if our formula is of special form, where phi is a formula which satisfies the first condition and the second condition for k equals 1. So there is only one permutation for all elements out of the diagonal. There is exactly one permutation which satisfies phi. Then we have reversibility. Now we'll see application. Applying this theorem, we show that betweenness relation, cyclic relation, and separation relation, definable in each linear order, are reversible, in fact. This is the answer to this question. What's going on with betweenness? Betweenness is reversible. Cyclic is reversible, and separation is reversible as well. What is betweenness? It is clear. What is cyclic? You take a linear order and make a circle of it, and this is ternary relation which, in fact, appears. Separation relation V0, V2, V1, V3. Separation says that these 4 points are in such position. These two intervals are in general position. Intersection and both differences are non-empty. That's it. On the cyclic order. The proof is simply in the previous slide you saw the definable relation will be reversible if the formula defining it is a special conjunction. So these are disjunction. Disjunction. These are disjunctions of very special formulas. For these formulas, V0 less than V1 less than V2, there is only one permutation of these variables which satisfies, which is satisfied the linear order. Total order. Now, these relations obtained by betweenness, cyclic, and separation are very important because Cameron proved that each set definable in the rationals. You take the rational line and observe all definable sets without parameters. Cameron showed that for each definable set, QD is first order be definable with exactly of one of the following structures, five structures. Trivial, Q with equality, Q with original relation, Q with betweenness, Q with cyclic, and Q is with that. So the previous result that these three relations are reversible can be proved by using the results of the following section about definability. This theorem is long. I omit it. So this is a generalization. Well, if you have alpha homogeneity, you will obtain in some way reversibility. This is a generalization, not alpha homogeneity, but that each partial isomorphism between two elements substructures of X can be extended not to automorphism, but to a mapping which preserves phi. So epimorphisms preserve positive formulas. Condensations preserve sigma plus formulas with non-equality, and so on. So this is a completely so this is another sufficient condition. Automorphism group is M set transitive if and only if for each two M element subsets of X, K, and H, there is a automorphism which maps one to another, and it is highly set transitive if and only if it is M set transitive for all positive integers. Now, a sufficient condition for reversibility of all definable relations is that this group is highly set transitive, for example, again, reals, but of course, also on other structures. Now, reversibility by interpretability by definability. So, what's going on with interpretations and by interpretations? Do they preserve reversibility? So, the point here is that if Y is reversible and X is interpretable in Y, when X is reversible too. Well, these are some syntactical conditions. First, that the formulas defining relations from Y in X are, and also the homotopy, are preserved under each condensation of X, and tau defining the domain of the interpretation, and eta G defining the corresponding equivalence are absolute. This must be preserved, this must be absolute under each condensation. Then X is a reversible structure. A consequence, a corollary, if Y is reversible and X a structure, if they are B-definable, one definable in other, and the formulas defining the relations from Y are preserved by each condensation, then the structure is reversible. So you will see an example, and reversibility is an invariant of this relation. This relation is by interpretability, which is unrelativized, which means that the domain is the whole domain. Injective, which means that these functions f and g are injective, and sigma plus with equality, which means that all the formulas defining all the things are positive, but non-inequality is allowed. This is an example, in fact, application of this theorem. If we take a random tournament, this is again countable homogeneous universal tournament, the Freise limit. Then we have original structure. Its language is binary. This is the first row. If we take one formula, eta, we observe this definable set. Then we have that this structure, new defined structure with definable relation, has RTN, of course, and its interpretation is the n. So, according to the previous theorem, if the original relation, this is tournament relation, is definable in the structure X, in this X with definable set, by such formula, then this definable set is reversible. Example. The point here is the following. You have random tournament, and the following two relations, the following two ternary relations are reversible. Well, the first one, which collects all the triples of this form, oriented triangle. So this is ternary relation, but it is reversible. It's not easy to show that, but the theorem helps. This is a first relation, and the other possibility that we have a transitive triple. So, in fact, the set of all triples which are linearly ordered by the random tournament relation is also reversible. And we can make a lot of examples because here is the general formula. So if we have a formula of this type, just a minute. So, random tournament, no. It is not here, okay. So, now we go to lines, to linear orders. What can we say about lines? The problem is, we recall, of course, that if X is a dense linear order without endpoints, plus, for example, Q plus R plus irrational, then all definable relations are reversible. The question is, for which linear orders we have such situation? Is it only the situation for dense linear order without endpoints? And restriction. First definition, a linear order is discrete if and only if each element except the smallest, if it exists, has an immediate predecessor. And each element except one, if it exists, has an immediate successor. The theorem is, if X is a linear order such that all definable relations are reversible, then it must be isomorphic to the following sum: m plus n plus l plus n, where m and l are in omega, it can be 0, of course, and L is either a dense linear order without endpoints or a discrete linear order. The definition of discrete is given. Hence, such order must be order minimum. This is a result of Pila and Steinhorn characterizing all minimal structures. They are finite sums. So omega, omega star, omega plus omega star plus omega, or Q, and these summons, there is finite sum of random elements, must be elementary equivalent to some of these 5 orders. So this is an all minimal structure. But it is not true that all minimal linear orders have the property that all reversible relations are, all definable relations are reversible. It's a trivial example. We take Q plus 2 plus Q, Q, 2, Q. There is A, there is B. So A is definable as the minimal element which has a successor. B is its successor. So the set minus infinity A is definable by A. So we have that the structure is not reversible because we again have infinite coinfinite set, so we have smaller isomorphic relation, it is not reversible. So in fact, these linear orders which satisfy that all definable relations are reversible are in fact stronger condition than all minimality, much stronger. Question is the converse true? And the answer is yes for dense linear orders for without endpoints. Which converse? Converse of the theorem. I would like to prove the theorem that for each infinite linear order we have definable sets, all definable sets are reversible if and only if it is of this form, with either Dlovec, either discrete. For Dlovec, dense linear orders without endpoints, we have, it is true, I will show it. And for discrete linear orders, which is very interesting because they seem much easier. This is, for example, integers, set. But they are not omega categorical, this is a problem. And here, for dense linear orders, I use, in fact, omega categoricity. There are two ingredients of the proof. The idea is to use the result about Q. Q, if I have dense linear order without points, Q is the prime model of this theory. And if I show that if I have a definable subset of Q, it translates in some way, it transforms into definable set of each elementary extension, then I'm finished the proof. This is the first ingredient. Structure X is almost highly set transitive if and only if it has the following property. There is a finite set K. So we have a structure, we have a finite set K, such that for each two finite sets P and Q, having equal intersection with K, there is an automorphism F of X which maps P to Q. This is almost set transitive. It is clear why. The model of this set K, which is fixed and finite set. So almost highly set transitivity, and for each almost highly set transitive relation structure, we have that all definable relations are reversible relations. Which almost highly set transitive linear orders are, or which linear orders have this property? This is a theorem. An infinite linear order is almost highly set transitive if and only if it can be represented as such sum, where in the middle we have two transitive linear orders. Two transitive linear orders, for example, Q plus R plus Q is not two transitive because we have uncountable segments, uncountable intervals in R. Okay, this theorem does not solve the problem completely, but it will help. If L is a two transitive linear order, then for the linear order m plus m plus n, we have this desired condition that all definable sets are reversible. And this is the another ingredient. If we have relational language and X an infinite L structure such that its cardinality is larger than the cardinality of the language, and if the theory of X is categorical of that cardinality, then for each formula, this is that story about elementary extensions, that for each formula phi and each elementary extension of X, if d phi is reversible in X, then d phi is reversible in Y. This is preserving by elementary extensions. This is the second ingredient. And now we have that if T is omega categorical, having only infinite models, and all definable sets are reversible for some countable model, then it holds for each model. So we can solve the problem on the level of countable models, and we have Q. It's excellent. We are finished. So the consequence of this is the following theorem. If we have a linear order isomorphic to the sum m plus L plus n, where L is a dense linear order without endpoints, then all definable relations are reversible structures. That's it. Thank you.
Thank you very much. Any questions? Comments? No? Well then, thanks again. I will remind you that on